one of the most common Java interview questions, and it is an advanced Java interview questions, is how does a Java hash map work? And they're not just asking how do you use the HashMap class from the Java Collections API, but they're asking how does it work internally. And the thing is, there's actually a little bit of a trick to this question because the implementation was changed in Java 8 to make it more efficient. So usually the person doing the interview wants to check if you know what that update is all about. Hi, I'm Cameron McKenzie. I'm the editor-in-chief over at theserverside.com, and I've helped coach thousands of people to get their first Java job and pass that Java interview. And I want to just explain to you how you should respond when asked, how does a Java hash map work? What I'd like to do in the next few minutes is quickly take you through just how you use a Java hash map, but we're not going to spend too much time on that. I'm then going to show you how the Java hash map is implemented behind the scenes. After that, I'm going to actually show you what the update was that makes these hash maps so much faster. And then I'd like to do a little bit of live coding with you where I go through a little bit of an example and we take a look at things like the hashCode method and when the equals method is called and how that hash map is actually working behind the scenes. But doing a little example of the hash map and just getting familiar with the code, that is what we're going to do next. Starting off, let's take a quick look at just how the HashMap class works. In order to use it, you've got to import java.util.hashmap, and you can create an instance just with HashMap, give it a variable name equals new HashMap. And a couple of things. Notice I put a number here. Behind the scenes, here's your first piece of information on how things work. Behind the scenes, the HashMap actually just uses an array. And if you can guess how many elements are going to be in that array, you can specify the size of that array right when you create the hash map. If you get close to that number, the hash map will expand its size, so it's not a hard limit. But if you want to stop the hash map from expanding all the time and wasting clock cycles, if you can peg the right hash map size when you create it, it's not a horrible idea. Now the other thing too, I mentioned that the hash map is part of the Collections API, and I don't know, if you want to be a stickler, it's not part of the Collections API because it actually doesn't implement the Collections interface. So there's a Collections interface that things like vector and ArrayList actually implement. If you actually dig into the HashMap class, you'll notice that it actually extends abstract map and abstract map extends map, and none of those actually implement that Collections interface. So if you want to be a real stickler, you can say, well, it's actually not really one of the Collections classes because, well, it doesn't implement that Collections interface. But what it does is it implements that map interface. And really, when we're working with a hash map, we're working with name value pair. So this is all of my favorites. Let's find out what my favorite movie is. So favorites.put name value pair. So I'm going to say my favorite movie is, and what's my favorite movie? We'll say it's Shrek, and there you go. We've got one element inside of our array. Now, here I've got two strings. A lot of people's first introduction to a hash map is putting strings as the name is on the left-hand side, the value is on the right-hand side. But you can actually have objects on both of those sides. It doesn't have to be a text string. Now, let me throw another couple of values in here. We'll throw in my favorite band, which is the lowest of the low. We'll throw in my favorite car, which is a Dodge Viper. My favorite YouTuber, which is Scrumptious. Control S, that saves. Now you can see kind of that idea of putting different values into that hash map, into that class that's going to keep track of all of this data. You can always do a system.out.println and print out the map. The toString, I think, just represents that as a funky little JSON string or something like that. So let's give that a run. Run as a Java application. Yeah, and you can see everything printed out there. The name value pair, car equals Viper, YouTuber equals Scrumptious. So that all looks good to me. And then, by the way, if you ever want to pull something out of that hash map, it's just a matter of saying, well, we'll do system.out.println, and we'll say favorites dot, and what do we have? A get for objects. So we'll get, and we'll get my favorite YouTuber And if I spelled everything correctly, we can always do a copy and paste just to confirm. That should print out scrumptious right after the actual map is printed out. So there you go. Those are the fundamentals, the very basics of working with a hash map. Now, the question that you get on Java interviews is not just the basics of how do you use the API, it's what's going on behind the scenes here in order to support that. Now that gets very, very interesting because it requires a bit of knowledge of the hashCode method, and it also requires a little bit of knowledge of the equals method. And by the way, just to give you an idea of the HashMap method, the hashCode method, every time you create an object in Java, each instance that you create gets assigned its own hash code. It's supposed to be a unique number. I think technically it's not universally unique, but it's going to be pretty rare for you to run into two numbers that are the same when you ask for an object's hash code. So if I created a string, handle equals Cameron MCNZ, that's my Twitter handle if you want to follow me over there, and then a system.out.println, and I said handle.hashCode. This is going to print out some long number, probably even put a negative in front of it, that represents that particular object. That becomes really important in a moment because you see, when the Java virtual machine, or computers for that matter, start organizing data, they don't like text strings, they don't like objects, they like numbers, and that number becomes very important when we start looking at the behind the scenes implementation of a hash map, and that is what we're going to take a look at next. So here's how a hash map works behind the scenes. When you create a hash map, what the Java virtual machine does is it creates a single dimensional array to hold all of your data, to hold everything that you want to put into your hash map. Now, there's a little bit of a problem with that because a single dimensional array can only hold one object per element, one object per bucket. And of course, when we put things into a hash map, it's always a key value pair, right? It's always two things. So here's how the Java virtual machine gets around that. It creates its own class called a node. And a node has four properties. You can probably guess the first two. One property points to the key. The other property points to the value when you put something into a hash map. The other property is actually the hash code of the key, right? Every time you have an object in Java, Java assigns it a unique key, a unique numerical identifier. Computers, the Java virtual machine, it much prefers working with numbers. So anytime it can use that hash code of an object rather than dealing with properties, it prefers it. So we've got the key, the value. It keeps track of the hash code of the key. And then it actually holds a reference to another node, which we'll get to in just a moment. Now, when you actually start adding objects into your hash map, what happens is the Java virtual machine will take a look at the key and the value. So, favorites.put movie Shrek. It will put movie and Shrek into this new node instance that it creates. It'll take a look at the hash code for movie, set that as the hash code, and then it'll take a look at your array. Let's just imagine we've got a 10-element array behind the scenes to support this hash map. So we've got a 10-element array, and when we put our first object into that array, our first name value pair, movie, Shrek, we find out that the hash code for the key movie is 9722. Well, what the Java virtual machine does is it says, well, I've got 10 elements, and well, the last number of this hash code is the number 2. What I'm going to do is I'm going to take that node object that I just created and put it into the third element, because array zero base counting, so the third element maps to the number 2. You get the idea, right? So it says, okay, the number 2 is the last number of the hash code. I've only got 10 elements, so I've only got 10 spots to choose from. Since the hash code ends in a number 2, I'm going to put it in bucket number 2. Zero base counting, that's the third bucket. Now, let's say another instance is created. So we now put into our hash map YouTuber Scrumptious. Well, the hash map is going to look at the hash code for scrumptious, and it'll say, oh, the hash code is 3053. And okay, so now we've got the hash code of 3053. We've got 10 buckets. The last number is a 3. I'll actually throw this new node object, this thing that holds all of that data, into bucket number 3, which is actually the 4th bucket because of zero-based counting. But again, you get the idea. So it's using that last number, right? That last number. And it's only using the last number because we only got 10 buckets. So we'll do a little modulus on the hash code and figure out where to put it. And then now let's assume, we get another one. What's your favorite food? It's ice cream. The key to food is 8320. The last number on that hash code is a 0. We've only got 10 spots. May as well just throw that right into element 0, right? Essentially the first element in the array, zero-based counting. And so that's how the Java virtual machine figures out where to put data. It also makes it really, really fast for the Java virtual machine to pull something out. Because imagine we now say, okay, I want to get out the information about my favorite food, which is ice cream. It looks up the hash code for the word food. It realizes that it ends in a 0. So it now knows, okay, the favorite food is what's in bucket 0, right? That hash code, the last number is the 0. We've only got 10, so we're doing a modulus of 10 to get the bucket number. Okay, we know that whatever's in bucket 0 maps to this. Pull it out. As I said, it's using numbers rather than using properties and all this other stuff. It's incredibly, incredibly efficient. So yeah, whenever you add something into a hash map behind the scenes, what's happening is the virtual machine is creating a node object. It's populating the node object with the hash code of the key, and the value. And then based on the last numbers of that hash code, it's mapping that to a corresponding bucket, a corresponding element in the array that it's using. So that is fundamentally how it works. Now, imagine we ended up adding something into our hash map and it ends up having a hash code of 9973. And we've already got something at 3053. So now all of a sudden that bucket's not empty, right? Like it's all nice, it's all fine and dandy when all the buckets are empty. Okay, there's a hash code ends in 0, we'll put it into bucket 0. Here's a hash code that ends in 3, we'll put it into bucket 3. All of a sudden you get another object that says it's the hash code 3. It's like, uh-oh, we've already got something in bucket 3. This is where that node reference comes in. So if we see the hash code is the number 3 and we've already got a node in the number 3, we still create a new node instance. We still take that new node instance and put it into bucket number 3. But that node property, okay, that node reference that the node itself has points to the other node in that bucket. So we end up getting a linked list. So yeah, the first element that went into element number 3, it's still there. We now put a new node, a new instance, a new key value pair into bucket number 3. We've now got 2 in there. And so what we do is that second instance, we use that node property to point to the first one. And so that is kind of, some of the behind the scenes stuff of how it's implemented. That's what happens when we get what they call a collision when we start putting things into our buckets. And we can potentially, depending on how many elements are being put into the array and what the size of the array is, we could end up with more and more and more elements all inside one bucket with all of these different nodes pointing to each other through that linked list that gets created. Now, there's a problem with that. It is a big problem with that. With a linked list, what ends up happening is if you want to go through the list and find a particular element in it, you've actually got to go through every element in the list. And in fact, what happens when we try and get an element out of a hash map and we end up getting sent to a bucket that's got multiple elements in it, what we do is we go through the elements one at a time. And we know that the hash code ends in 3, but let's just say that, we've got a whole bunch of things where the hash code ends in 3, but we're specifically looking for the key value pair where the key was movie. We pull that linked list and then we start doing a dot equals comparison on each node saying, okay, I know that, the favorite movie is going to be somewhere in this linked list. So we get the list and then one element at a time, one node at a time, we start saying, does the key dot equals movie? Does the keys, name, does the key dot equal movie? We want to do an equals comparison, not just a hash code. And we do that until we find it. Now, if we've got 10, 20, 30 elements linked together, there's a possibility that the last one we're going after is going to be the last one in the list. And so that ends up becoming a very, very slow search. What they did in Java 8 was they said, if we hit the critical mass of 8 elements in this linked list, what we're going to do is we're going to break the linked list and create a binary tree. And the thing about a binary tree is that you can do very, very fast searching on it. So, for example, if I had a binary tree with 1, 2, 3, 4, 5, 6, 7, 8, 9 elements in it, and potentially I wanted to find element 8271, I wouldn't have to search through all 9. With a binary tree, what you can do is you can take a look at the first node, and in this case, it might be 8051, and then you can say, you know what, it's actually higher than that. And then you look at the next node and you do a comparison. You say, okay, it's actually going to be lower than that one. And then you keep going through the tree. You keep breaking the tree in half on every search. That's a binary search through the tree, and that's extremely efficient. It's the fastest type of search that you can do with a group of data. And so that was the big change that they made with Java 8. So I've put together this little code example that I really hope you actually code on your own and play around with a little bit, because I think it really drives home how the HashMap works and how it works with dot equals, dot hashcode, and the various buckets that get created behind the scenes. I've created a class here that's going to represent the key in a key value pair, right? When you put something to a hash map, you'll say hashmap.put car Viper, and car would be the key, Viper would be the value. In this case, I'm not going to put car as the key. I'm going to create a hash and key as the key, and this hash and key will have the key car, and it'll also have a hash code that I'm going to specify. I'm not going to allow the virtual machine to create a key for a hash code for the key. I'm going to specify it. The reason I'm going to specify it is it's going to allow me to create multiple keys with the same number and simulate a collision. And so you can see there's a constructor here, hash and key, which takes the hash code and the key, and I get to assign both of those. Now, behind the scenes, the virtual machine calls the hash code method of the class of the key that's put in as the key value pair. But you can override that, right? So you can see that I've overridden that hash code method here. And as I've overridden it, I'm just returning that value that I specified for the key. I can make it a random number, but I can put every key in with the same number as well and see what type of havoc that creates. Now, as we discussed earlier, bucket selection, index selection in that behind the scenes array is determined by the hash code of the key. However, if there's more than one element in that array, more than one node, more than one set of values inside that bucket in that array, well, we can identify which bucket to go to with hash code, but we have to do a dot equals comparison on all of the different nodes that might be linked together in there. So I've overridden the equals method as well, and I just put a printout in there saying calling the equals method and what object we're calling the equals method for, and then we just do the equals method. Similarly, in that hashcode method, I printed out calling hashcode so we can see when the hashcode actually gets called. Now, what else do I have there? The toString method, which will make things easier. And then I've got the main method here. Okay, so I create the hash map, and the hash map has the hash and key is the key. That's the class we've been looking at. And then just a string for the value. So you can see I put my first hash and key in. The hash and key is 1 in Andrew, and the value is alpha. Then I put a second hash and key. The hash is 2. The key is Betty. The value for the key is Betty. And then the value is actually Bravo. Hash and key 3 Claire, and then the value is Charlie. And then hash and key 4 Darcy, and the value is Devo. And so you kind of see how this is getting put in there, and I try to make it alphabetical so you can kind of keep track of the order. Now in this case, every single key has a hash code that is unique, 1, 2, 3, and 4. So as I put elements into this hash map, really there shouldn't be any problem putting things in. And if I pull things out, the only thing we should ever have to take a look at is the hash map, because the array behind the scenes is only ever going to have one element, one node, one piece of data per element in the array. So if I know which element in the array to go to, say when I look up a value based on a property, I will get to the bucket right away. There'll only be one thing and then there's no problem. So let's do this. Let's run this code. So I'll run this as a Java application. And when this code runs, let's take a quick look at it here. Maybe even throw that up there. Give me a moment to do some formatting. Notice that when we store key 1, we call hashCode, and that tells us to put it in the element 1 in the array. Key 2, we call hashCode, that puts it in element 2 of the array. 3, third element. 4, fourth element. Everything is fine. Even when we want to go and find the key value associated with HP here, so we've got a hash key named HP, we try and pull that out again a little bit later. We'll call that Darcy. Darcy and Darcy there to make it look a little bit more obvious, just which key we're pulling out there. So we put in Darcy, we now pull that out, and when we pull that out again, we only need that hashCode call. It tells us which bucket in the array to go to. We pull out the node that's stored there and get the property from it, and then the property associated with Darcy is Devo. So this is the happy path. This is perfect when there's no collisions. Now, here's the thing. We can force the same hash key, hash code for each key. So notice how over in the console, we only ever called hashCode in order to search for an element or even to figure out where to place an element inside of our array. Well, now watch this. I've set everything to have the same ID of 1. Watch the madness. Okay, we put the first one in. Okay, all we had to do was call hashCode because there was no conflict. We put the second one in, but that second one does have a conflict. So now we actually have to get that first element, and then we have to actually go through what's already in there. So we've got to call for equals on Andrew. Add the third one in. Okay, now we call the hashCode on the third one. It's 1. Uh-oh, problem now. We've actually got to put that into that third element in the array, but we're going to have to go over the other elements that are already in that same bucket, which is Andrew and Betty. We now store the key for 4. Again, that's hashCode. Now we got to go Andrew, Betty, and Claire again. And so now we're putting it in, but it's not good enough just to have the hashCode. Now we have to go through each element in that array and then figure out whether that element is in there or not already. And then if it's not already in there, then we add it in. And that's what that equals is doing there, right? So you put a new element into a bucket. What happens is we say, okay, we're putting something into bucket number 1. Okay, there's 3 things in bucket number 1. let's make sure that this thing we're putting in there doesn't already exist in there, right? Let's make sure there's, if you're putting something with a key of Betty, let's make sure that something doesn't already exist in there with a key of Betty. So that is why we're forcing that equals. It's also really interesting when we go in and we try and get Darcy, right? That Darcy key was the fourth one that was put in there. So we say, okay, let's get Darcy. That is now key number 1, which takes us to a bucket which has 4 things in it. So the first element in that bucket, we have to say, okay, I know that we're going to bucket number 1. We're looking for some of the key of Darcy. Hey, that first element in there, do you match the key of Darcy? Do you have a dot equals for Darcy that's true? And it says, no, I'm Andrew. And we go to the next one. I know I'm Betty. Next one, no, I'm Claire. And the next one's like, okay, that's the last one left there. Then that's got to be it. And then we pull that out and then we get Devo. And so that is the chain of events if we force this to have the same key each time. Now let's just take a look at this again when every key is unique. Right? It's a nice comparison. We don't have any of those equals calls. It's all just hash code. So there you go. Play around with this code. There's a link in the description that will help you get the code for this example. As I said, and I think this really drives home how that HashMap is working behind the scenes. Now, if you enjoyed that tutorial, why don't you head over to the serverside.com. I'm the editor-in-chief over there. We got lots of great tutorials on Java, on Spring Boot, on microservices development, on Git, on GitHub, on Scrum and Agile. If you're interested in my personal antics, you can always follow me on Twitter at CameronMCNZ. I have written a couple of books, and you can see back there, well, what is WebSphere doesn't sell too well anymore. There's Hibernate Made Easy, all about working with Hibernate and JPA. There is also Pickering of Springfield, which is a book that I wrote about the fictional hometown of The Simpsons. And then also you'll see Darcy DeClute, Scrum Master Certification Guide. A lot of people have been reading that book and scoring 100% on the product owner or Scrum Master certification exam. So if you're agile and working with Scrum and you really want to enhance your career, I highly recommend picking up that book. And then finally, if you're watching this on YouTube, then why don't you subscribe on YouTube?